All right, new day, new video. So today's video about the derivative is based on something that's synonymous with a topic in my last video, the instantaneous rate of change. Okay. All right. So the derivative, what we'll learn about now is technically different than the instantaneous rate of change. But if you want to think about them as the same concept for right now, I don't think it will hurt anything. Okay. Um, I'll explain how these are different and how they're the same though throughout the video as we go through it. It's complicated. I'll warn you. Uh, I think that the instantaneous rate of change, what that is, what the derivative is, what they tell you, why, say, an economist might care about them, are all fairly complicated topics, all right, with a lot of information, and it's very hard every time I do this to decide what's the best place to start explaining what they are because it feels like no matter where I start, it gets a little bit awkward as I go through it, and I feel like I should have started somewhere else. So but that's like no matter where I start, that's how I feel about it. There's no perfect place to do it because it's complicated. So you might this might be something that you have to watch the video, you have to think about it a little bit, you have to ask some questions, and like anything that is complex and technical in math or economics or finance, it might not sink in right away the very first time you hear it, and this is one of those things. Now, there are some things that are easy about it, and we'll talk about those things too. But if you feel like you're getting lost somewhere, you don't understand something, then ask about it, and that will start a conversation that will lead you to understanding all of it, I think. Okay. All right. So, the instantaneous rate of change. Yes, covered in a previous video. I think it'd be necessary to understand that first before talking about the derivative. Okay. Now, uh, let's do like this. The notation. Math is full of symbols, and we have to know what the symbols mean. That's what notation refers to. So let's say f of x is some kind of function, some kind of formula. And this thing right here, do you see it's a f with an apostrophe x? Okay, that's what the derivative is. And whenever we um, write the f apostrophe to differentiate from the f of x, the f apostrophe is read f prime. Okay, so that's how you read it. That's how you say it out loud, and I'll refer to it that way. But that's what the derivative will be. Okay, so there's a function, and then there's this thing called the derivative. All right. Okay. And its symbol is f apostrophe x, read out loud f prime of x. Now, we've seen an example of this because the derivative tells you the instantaneous rate of change in a function. So, like, here's a good example. Here's an example at least I brought up in an earlier video, okay, that if we had a function r of x that tells you the revenue that you get from selling x units of some product, then its derivative, the instantaneous rate of change, would tell you it would be a number that tells you the change in revenue over the change in production, and we call that the marginal revenue. Okay, so yes, if r is a revenue function, r prime is derivative would be the marginal revenue, which tells you how the revenue and production change together. Okay, so there's like two sides of this coin. We got a function that tells you what the revenue is, and then we've got this other function called the derivative that tells you how changes in production cause changes in revenue. Okay? It might be that a small change in production causes a big change in revenue, or it might be that a small change in production causes an even smaller change in revenue. Who knows? But that's what that tells you. Now, I think that's an important thing to keep in mind. The function tells you what the revenue is. The derivative tells you how the revenue and production change together. All right, now let's take an example of that. If I had some revenue function, and if, say, like in my last video, I found the instantaneous rate of change, which will be the same thing as what the derivative tells us, and I found it to be 7. And that would tell me this. At a production level of 900 units, each additional unit produced and sold will yield an additional $7 in revenue. We could think about it that way. It tells me that the change in production at the production level of 900 is 1, and the change in revenue as a result is $7. Okay. Now, I want to weave in some other things that will become important as we go a little bit further. And that is that suppose that we had the revenue curve. Now, economists really like to talk about curves and graphs. And if you've taken economics at all yet, then one of the very first things is, I guess this would be macroeconomics, but one of the very first things you learn about is the supply and demand curves and all the concepts related to that. So yes, economists love graphs, curves, and the information that's on them. So if I had the revenue curve, and if I found that the derivative of the revenue function at the point on the curve where the production is 900 was 7, then that's telling me, like, basically rise over run on the curve. It says that, okay, well, right there, the run is 1, so that's the change in production, and the rise is 7. That's the resulting change in revenue. Okay, it's telling me that feature of the curve right there. It's telling me that if you're on the revenue curve right there, bumping up the production by 1, that's going this way, causes me to bump up the revenue by 7. That's going this way. Okay, so it's like all really the same thing. Whether I describe it like this, or whether I show you the curve here and I say a change in x is 1, and that will result in a change in r of 7. Okay. Remember the delta symbol, the triangle symbol, delta means change. All right. So now that's some new concepts weaved in with some concepts from the last video. Okay. Now, let's go to the next thing. How do you calculate the derivative? Okay. So I guess I should have, when I made the notes, should have put it like that. Because, like, think about it now. We're doing and the derivative. Okay, so it will tell us the instantaneous rate of change of a function. It's like same thing that's talked about in a prior video. The symbols for it, okay, f prime was the symbol for the derivative of a function. All right, and then, well, how do you calculate it? Well, that's the part I haven't got to yet. So there are three ways. Let's talk about. Okay, so the first is that you can use this formula here, which is a formula that I had used in an example in my last video, I think. It was either the last video or the video before. The derivative can be calculated as the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, now remember, the derivative tells us how two variables change together. So like if you have a revenue function, it's going to be, the derivative will tell you the change in revenue r variable over the change in production x variable. Okay, so if this formula, if we dissect it and you say, what does that, how does that formula tell us anything? Well, okay, I mean, this top part tells you the change in the variable y. If, like, say for just some general function, y is the output variable. And then down here, that h is the change in the variable x. How's that? Well, see, x here, x plus h. So that's like x plus a little bit, okay? So that's the change in x down there. And then this h goes to 0 is what makes it instantaneous, or it's the rate of change between y and x over some small change in x. That's why the instantaneous rate of change is called instantaneous. The root of the word instantaneous is instant, okay? Meaning very, very small, like almost nothing duration of time, all right? But anyway, so like we're getting too deep into it. So, okay, it tells you the change in y over the change in x over very small changes in x. That's what makes it a rate of change. It tells you the change between two variables. All right, So that's one way you can do it, that formula. And I'll show you an example in a minute of how we can use that formula. Another thing is rules, okay? There are rules for calculating the derivative of certain kinds of functions. If you took any calculus any time before in your life, then maybe you've learned some of the rules. Okay, so there are rules too. So let's say this semester, though, we'll probably, test 1 will be reserved for finding the derivative this way, because if there's not a rule for a particular function, then we'll have to do it like that. Okay, so test 1 will be to do it this way. Okay, and then we'll learn the rules for test 2. And I'll make an official announcement about this, but this is what I have planned for right now. Okay, so once the test gets a little closer, I'll say, by the way, to find the derivative, we'll need to use this is called the difference quotient. I told you that there is a lot of information packed into this topic. So that's called the difference quotient. So I might say, well, we'll have to find the derivative by the difference quotient. Okay, then there are some rules. Okay, then we'll, like from test 2 onward, we'll probably just do the rules. Then there are like calculators and technology to find derivatives for you, obviously. Okay, and like, you know, it's like I'm okay with it sometimes if we do that way too. Okay, but not for this test. Like we'll talk about using calculators and other technology at the point of test 2 onward. But you know, I do think that, and it's not just my opinion, it's how I'm obligated to teach the class, that we should learn everything. Okay, like I think it's good that you learn stuff, and for the scope of what you might learn in economics and finance and beyond, maybe that I'll learn all 3 aspects of the derivative. Okay. Plus, if like there aren't rules, and if a calculator or technology can't do it either, this is like our last resort that always works. Okay. All right. So even if it's not easy, it always works. Now, so let's do this. Let's see, go down here, and I wanted to keep tying it in with that other video, because like I'm making this now thinking that the previous videos you watched it and you're okay with it, because I always say, like, here's the video, if you have questions, ask the questions, and if I don't hear anything, then I'll take it it's okay, because what else could I assume? But you know, I did have that problem with the revenue function, and yeah, so like here, all right, here's that same thing right there, but adapted for the revenue function. And of course, like if the R variable is revenue, then on the top is the change in revenue, and down here, if the X variable is actually production, then that right there is the change in production. And this part, limit H goes to 0, is what makes it instantaneous. Okay, that's what makes it apply over small changes in production. Okay, now let's do an example. Let's do this. So let's forget about all the concepts for a moment, because I think the concepts make this difficult, right? I said that, I started the video that way. I said that, yes, this is a complicated topic. It's very subtle, it can be hard to understand. All right, let's talk about now just how do you do this? How do you find the derivative through this process? Okay, that thing right there. How do you do that? Now I'll focus on just that. Okay, so let's say that we have this function. F of x is negative 4 over x. What is f prime of x? Which is the derivative, right? Remember f prime, the derivative. So if the question had alternately said, what is the derivative of negative 4 over x? Then same thing. Here's how you find that. It's the limit, at least for test 1, okay? And then we'll talk about other ways to do this, test 2 and beyond, but it's the limit as h goes to 0, f of x plus h minus f of x over h. Okay, so that's what we need to do. Here's my technique, all right? And this is my technique. If I had to do it this way, this is how I would do it. You could do it, you could rearrange this if you wanted to, but my technique is to first simplify this part, the f of x plus h minus f of x over h part, okay? That's the first part. I'll simplify that to the point that it can get no simpler. And then after that's done, I'll apply the limit. All right, so I'm going to do it that way. What you're about to see is me doing it that way. All right, now, so first part is we'll simplify this difference quotient. Remember, this is called the difference quotient. And that's f of x plus h minus f of x over h. That's this part, okay? Because remember, my function is f of x, okay? If I were to put x plus h, substitute in for the x in this function, it would be negative 4 over x plus h. So that's f of x plus h minus f of x. Well, f of x is the function in its given form. That's negative 4 over x, so that's this part. Divided by h. Okay, so that's my starting point. That's f of x plus h minus f of x over h. Now, if I'm going to simplify this, the way that I simplify this depends on what I have, okay? But it would be a matter of just reducing it as much as possible. Now, to simplify this, the way that I would need to do it is subtract these fractions and divide, okay? Let me give you another example. Suppose I had 1/2 minus 1/3 over 4. That's a lot like what I'm dealing with now, okay? In that I have this fraction minus this one divided by that whole number. By analogy, I'm saying this and what I'm about to show you is just like this. Okay. Maybe we should run through then how we would calculate this number without a calculator, all right? How would you figure out what this was? 1/2 minus 1/3 all divided by 4. Well, my first step would be to subtract those two fractions. What is 1/2 minus 1/3? Well, I would have to get a lowest common denominator, which is 2 times 3, or in other words, 6, okay? And the way I would do that is I would take 1/2 and I would multiply 3 over 3, okay? And then I would take 1/3 and I multiply by 2 over 2. So that's how I get that common denominator of 6, all right? 3 over 3, 2 over 2. That'll get me over 6 in each case. All right. So what am I going to have right there? 3 over 6. And then what am I going to have here? 2 over 6. Okay. Now I can tell you what 3 over 6 minus 2 over 6 is. How do you subtract fractions? Well, when you have a common denominator, we'll do this numerator, 3, minus that one, 2 over that common denominator, 6. Okay, so like that. Let's continue right here. So that would give me, so 3 minus 2, that's 1 over 6 over 4. All right, what's next? Well, now I'm dividing. I'm going to try to say, what's 1 over 6 divided by 4? Well, the way you divide two fractions is we multiply by the reciprocal. So I need to see this like this right here. So look at it this way. So I have 1 over 6 divided by 4 over 1. That's how I'm going to interpret, for the sake of division, 1 over 6 divided by 4. Okay? So what did I say a minute ago? Dividing fractions means multiply by the reciprocal. So I would take 1 over 6 and I multiply, instead of divide, by the reciprocal of 4 over 1, which is 1 over 4. So that's 1 over 24. So multiply fractions straight across. Okay, now what I'm about to do on this difference quotient, you know, this right here is the same. It's the same exact sequence of steps, okay? So that's why I want to show you this first, because if we got stuck at some point over there, if there's some part of it you don't understand, it'd come back to knowing how to do this first, probably, all right? Okay, so let's see. Let's go back and I'll say, okay, I need to subtract these, and that means I need a common denominator, and the common denominator is LCD is x times x plus h. All right, so I multiply this fraction by x over x, giving me negative 4x over x times x plus h. And I multiply this fraction by x plus h over x plus h, giving me this fraction. Okay, now I have a common denominator. Next step. Okay, but what did I do over here? Same sequence of steps, same order. There's really, even though it looks like they're very different and one's more complicated than the other, the problem I'm doing over there is no different than this one. Okay, so next I subtract. Okay, so I take this, negative 4x, minus this, negative 4x plus h, all over the common denominator of x times x plus h. But when I subtract a negative, that amounts to adding, so it will be negative 4x plus 4 times x plus h over x plus h. Okay, so now I've subtracted. What was the next step? Well, how about, let's reduce this a little bit before we go any further. Like, what's that? I think some of this stuff will cancel up here. That's why I'm focused in on it. So I have negative 4x, but what if I distribute this 4 right here? I'm going to get plus 4x plus 4h, see? And then these negative 4x and positive 4x cancel, so all I'm left with is 4h. You see that? Okay, so that's after working out this top part. Okay. Now, what was after that? Now I'm to the point where I'm dividing, and I have this fraction up here divide by h, but h, it looks to me like a whole number, so I'll put a 1 under it, and let's go like that. And so this fraction divided by this one would be the same as this fraction times the reciprocal of this one. What's the reciprocal of h divided by 1? It's 1 divided by h. Okay. Now, I could multiply these fractions by multiplying straight across, but I'll notice that I've got an h over an h. I got an h on top, h on bottom. So when I multiply, I get 4 times 1, 4 over x plus h times 1, x plus h. There it is. Okay, so I've simplified it at that point. Done, simple. I mean, there's nothing else I could do to make this any simpler or reduced or canceled beyond what it is right now. So my second step was to apply the limit h goes to 0 to whatever you got up there. So that's the limit as h goes to 0, 4 over x times x plus h. If h goes to 0, it becomes 0, okay, in this case. And I get 4 on top, and I get x times x, which is x squared on the bottom. Okay, so I applied the limit, and I got this, 4 over x squared. That's the derivative, okay? So this right here is the derivative. It's the thing that tells you how y and x change together for that function we started with up there, given that x changes by a very small amount. Okay. Now, so that's the process of finding the derivative by the difference quotient, which will be the way that we do this for the first test. Okay? Yeah, for test 1, we'll find derivatives that way to prove we know how to do it. From then on, we'll use rules and technology to do it. Okay, now, next thing that we do is, well, let's look at it this way. Remember, in this example, I said if I find the R, the revenue function, and if I find the derivative of it, it tells me how production and revenue change together, okay? If the marginal revenue of R prime is 7, it means if we increase production by 1, we'll increase revenue by $7, let's say. That's a number, okay? It tells me if production changes by this amount, revenue will change by this amount. And that gives me the numbers for what they are. 7 being 7 over 1, all right? Production changed by 1, revenue changed by 7. Okay. But this is not a number. So how does it tell me how the variables are changing together? Well, you have to say what the variables are most of the time. So next thing might be something like this. If we have the original function, what is the derivative if x is 2 and if x is 0 and if x is 1? Okay, like we'll find out what the derivative is for different values. You may find that this is the marginal revenue or the derivative of the revenue function when production's 900. At different levels of production, you might find that the derivative is different. At different levels of production, you might find that the way revenue increases from increased production beyond that point varies. It depends on what you're starting at. What's the production? What are we changing or increasing from? So generally, like derivatives will have different values at different values of the independent variable, the input variable. In this case, production. All right. So yes, generally, in order for the derivative to be a number, I have to tell you what the variable, the independent variable, the input variable in the function is. In this case, it's x. Okay. So all right, let's see. So it says, can you calculate f prime of 2, f prime of 0, f prime of 1? So I got f of x to be, for this function, so I just did that part, that's going to be 4 over x squared. Okay, so there's my derivative. Here's the function. It tells me what y is if you tell me what x is, and this is the derivative. It tells me how y and x change together. All right. So let's see, that's the derivative, and apparently it's got an x in it, and so if you plug in x to be 2, or if you plug in x to be 0, or if you plug in x to be 1, you'll get different numbers. Okay, so let's see, f prime of 2, well, if this is my derivative, it's going to be 4 over 2 squared, which is 4 over 4, which is 1. Okay, so f prime of 2 is 1, or the derivative is 1 if x is 2. What about, let's do f prime of 1 next. See this one over here? So that'd be 4 over 1 squared. See that? So my derivative is 4 over x squared. So that's going to be 4 over 1, so that's 4. All right, so if x is 1, the derivative is 4, or f prime of 1 is 4. And then last, this 0 right there, so that's not going to work because I'll have to do 4 over 0 squared, but that's 4 over 0, and that is meaningless. It's an impossible calculation. It's undefined. I put UND as if to say undefined because I'm running out of room. All right, so we've got 3 things here. I've got the function. I have the derivative of the function, and then I have what the derivative is at different values of x. All right, so that's like the scope of, for the most part, for the video today. I did want to talk about, because I want to weave in some things that are coming up that if you think a little bit about it now will make it easier for some of the topics ahead, okay? Whoops. Okay, so why is the derivative different at different points? I want you to think about this. So, like, for example, here's my function, here's my derivative. For every function, there's only one derivative, but that derivative could take different values at different points. And by points, I mean at different x's. Why does it do that? Okay, I foreshadowed to this a little bit a minute ago when I said probably the way that it works with a revenue function in reality is that increasing revenue will not always, increasing production will not always increase revenue in the same way. Okay, so it might be that I increase revenue at one level of production, or I increase production at one level of production and I get a fairly big increase in revenue. But if I increase production at another level of production, I get a much smaller corresponding increase in revenue. It might be that way. It might be that the way that the revenue increases as a response to change in production varies across the whole range of production that's possible. So you might think, well, just like naturally, it kind of feels like the derivative wouldn't always be the same number all the time, right? So you might just naturally say, well, of course, like the derivative is going to be different at different points because it just doesn't make sense for it to be the same everywhere. Okay, but to further appeal to that intuition, if you have it, or to try to show you why it would be like that if you're not sure, I'll go back to this function. So here's the function I was working with a minute ago. It's negative 4 over x. And here's what we found. F prime 0 is undefined. F prime 1 is 4. F prime 2 is 1. Okay, so why is it undefined and 4 and 1? Well, it depends on what the curve or the function looks like as a graph. Now, I'll give you this as a graph to weave in some things that are coming up, but also to economists love curves and functions and graphs and all that. So I'm going to show you the graph. So here's the curve, negative 4 over x. Okay, it looks like this. Here is the point where x is 1, right there, because that's what that means. And here's the point where x is 2, right there, because that's what that means. Okay. Now notice that the curve is steeper here than it is here. Like if you imagine like climbing up a hill that was shaped just like this curve, it would be a lot easier to walk up the hill here than it would be here, and especially there. Now, why is the derivative different at those points? Well, the derivative tells you how the variables in the function change together. So each of these tells me the change in y over the change in x. That's why if I was dealing with that revenue function from earlier, it would be the change in revenue that results from change in production. Okay, so these tell me, because it's not a revenue function and there's just x and y in this case, change in y over change in x. So if at 1, at the place where x is 1, which is right here, if the derivative is 4, then that tells me that, well, at that spot on this curve, if you go over 1, you'll have to go up 4. That's how steep it is. So it's like it tells me the slope of the curve. In addition to telling me how if x changes by 1, y has to change by 4, that is also sounding like the slope or steepness of the curve. So the curve is such that its slope is 4 at this spot. Go over 1, go up 4. That's the nature of the curve. That's how the variables have to change together at that point. And then over here at the point where x is 2, if the derivative is 1, then that means that if I go over 1, I have to go up 1. Okay? Why is that? Well, because the derivative tells you how y and x change together. If that number's 1, it's got to be that it's 1 over 1. So this one is like 4 over 1. Whoops, that's a 1. And 1 over 1. Okay, 4 over 1, 1 over 1. 4 over 1, 1 over 1. Because the curve's not as steep there. Okay, the curve is such and the variables are such at this point that if x changes by 1, y changes by 1 as well. And here we're a lot steeper, so the variables on the curve is such right there that if x changes by 1, y changes by 4. Okay. Now, so that's why the derivative is different at different points. It's because it turns out to measure the slope of the curve in addition to everything else that I've said about it. And a curve is such that it might be steeper at one point than at another point. Okay. Now, what about the undefined? Like, why is f of 0 undefined? Well, I mean, if no matter how you interpret the derivative, if you think it tells you how the variables change together, or if you're thinking of it that it tells you the slope of the curve, it tells you the rise and the run at any particular point, then this curve is such that there is no point on the graph at x is equal to 0. I mean, there just isn't. I mean, the curve has a vertical asymptote at the y-axis. There are no points on the graph at x is equal to 0. So there can't be any way to measure how the variables change together there, because the variable being 0 is impossible. So this is undefined by proxy, all right? Or as a result from the fact that the curve can't be 0 anyway. All right, now, so that's everything for this video. There are some things relevant to the topic as it is for the assignment I'm making the video for. There's some things we've done that are for topics that are coming up, okay? But it will give you a lot to think about, like I told you. And so the way it works, if you're learning any sort of complicated math, science, social science, economics, whatever, like once it gets complicated enough, once it gets advanced enough, then you're probably not going to understand it right away, and it will probably benefit you a lot to ask some questions, to see what other people think, to give it some of your own thought, etc. So I'm here if you need help, and I'll be posting another video tomorrow.